So just as a refresher, so in today's lab, we're going to be determining the formula of copper gluconate, which is the formula copper C6H11OXN. We're going to measure the mass of copper gluconate, which we found experimentally to be 1.4 grams. Your value may be different. When we dissolve it in water, when we treat copper gluconate with water, we generate a solution of copper ions and gluconate ions. We can then react the copper with aluminum to convert the copper ions into solid copper that we are then going to weigh. A critical feature of this experiment is all the copper generated from the reaction of copper gluconate came from our copper gluconate. So then we're going to weigh our copper gluconate. We are then going to treat our solution of copper gluconate in water with aluminum. It will generate copper. We're going to determine the mass of the copper by subtracting the mass of our empty cup from the mass of our cup plus the copper. We found in our experiment the mass of our cup plus copper was 2.6 grams. The mass of our empty cup was 2.4 grams. So our mass of copper is 0.2 grams. Now, we know that looking at our copper gluconate, the mass of copper gluconate is composed of copper and gluconate. So then we know the grams of copper gluconate are equal to the grams of copper plus the grams of gluconate. So we can obtain the mass of gluconate via subtraction. Wonderful. Is everyone following so far with this overview? Does this overview make sense so far on how we've processed our experimental data? Does that make sense so far with how we processed our experimental data? Okay. Now, through a series of algebraic manipulations, we know that given the mass of copper, we can do a mass mole conversion and calculate the moles of copper by taking the mass of copper over the molar mass. This is what we'll need for later. Okay, that's the easy part. These are the easy calculations. Now let's move to something a little more involved. So we know, looking at the formula for gluconate, that the total mass of all of our elements is equal to the mass of gluconate. Wonderful. Now what we can do is we can write the moles, we can write the mass of each of our element in terms of the moles. This is a mass to mole conversion, just multiplying by the molar mass. That much is established. Now, we can then rewrite each of these equations in terms of the moles of oxygen. So we can rewrite the moles of each of our element in terms of the moles of oxygen or the moles of carbon, whatever we prefer. Just something we can do looking at this equation. Now, we can write out an expansive equation showing that our total mass, so this is our total mass, is the sum of the mass of each of our elements. But we get stuck dealing with X and N. So what we can do is we can look at our formula, look at gluconate, and we can say, well, we know that the molar mass of gluconate is equal to the grams of gluconate, that we know, and the moles of gluconate, which we can figure out. So we plug in our grams of gluconate. Now for the moles of gluconate, we have to use our expression for the total mass and the total moles. So we know that the total mass is the sum of the mass of each of our elements, okay? And we can write the moles of each of our elements in terms of oxygen. That works wonderfully. Now, what we also know is that the molar mass, which is equal to the grams of gluconate per mole of gluconate, is equal to the molar mass of carbon times the number of carbon atoms plus the molar mass of oxygen times the number of oxygen atoms plus the molar mass of hydrogen times the number of hydrogen atoms. These molar masses we can all look up from the periodic table, which we can plug in for the atomic mass. Now, the number of oxygen atoms in gluconate is represented by X. So we have this expression where our molar mass is equal to 72 plus 11, which is 83 gram per mole plus 16 gram per mole times X. Okay. This molar mass, this expression for our molar mass is also equal to the grams of gluconate over the moles of gluconate. And we know that the moles of gluconate are equal to the moles of copper times N. Why? Our formula is of the form Cu C6H11OXN. So for every 1 mole of copper, we have N moles of gluconate. Does that make sense so far? Does everyone get where this relationship comes from? Is this making a little bit more sense now? Can I get some responses in the chat just to see if anyone has any questions so far? Everyone understanding so far? Okay. Now, what's tricky about this problem is the fact that you have to guess what N is. So you're going to guess N to be 1, 2, or 3 for copper, because copper can be either +1, +2, or +3. So now, we are going to write and plug in the numbers into this expression. So we have our 83 grams per mole plus 16 gram per mole times X. This is our expression for the molar mass. And that is equal to 1.2 grams, which is our grams of gluconate, over our moles of copper times N. And what you're going to do is you're going to guess values of N for N equals 1 and N equals 2. So punching this data into our calculator for N equals 1, let's punch that into our calculator really quickly. We get 18.6375 that we round to the nearest whole number, which would be 19. Alternatively, for N is equal to 2, we take 381.2 divided by 2 minus 83 gram per mole divided by 16, and that in turn gives us 6.725 that we round to 7, the nearest whole number, because we can't have a half an atom in the formula. And in this case, we know the literature value for copper gluconate. So in comparing our two proposed formulas, so our N equals 1 formula and our N equals 2 formula, we see that comparing to our literature value, which is of copper gluconate, which is copper C6H11O72, that the N equals 2 guess matches the literature value. As the data that you get in this experiment is not perfect, you will often have to round your value of x to the nearest whole number. Now, if we are doing this super quantitatively, we'd want a perfect match with no rounding at the end of our calculations. But of course, we're doing chemistry with a lab box, so it won't be a perfect match. So in the end, we were able to report the following formula for copper gluconate. And the equation that you're going to use is right here. I would check your worked example in the experiment 4 module. Note, in terms of the base equation that you're using, it's all the way up here, and you plug in your raw values for the grams of gluconate and the moles of copper. So this experiment, it's a lot of algebra in the background, but once we have all the algebra down, it simplifies to a very easy to use equation. Is everyone comfortable using the equation to solve this lab? Is everyone comfortable using the equation to solve this lab with their own data set? Does everyone understand the calculations I used for my data set? Does this make sense so far to everyone? Any questions so far? In the earlier attempts, I was trying to get a nice, clean algebraic solution without guessing, but this is one of the few empirical formula problems where they want you to guess values of n, just to make the math and the algebra less tiresome. Would everyone feel comfortable using this equation that I put a star next to with their data? So with that said, that's the end of our lab lecture and calculation session. If you're following along at home, your calculations should look exactly identical to mine if you're using the same data set. I'd like you, if you completed this calculation and collected data from your lab box, I'd like you to complete the calculations using your own lab box data and attach your calculations as a screenshot to your report. You don't have to worry about showing how you got the equation. Just show me the equation before you plug in your variables, the equation after you plug in your variables, label your variables, and then I'd like you to justify which value of n and x is correct by comparing and calculating percent error. Does that make sense to everyone? With that said, that's the end of our lab lecture and calculation section.